So today, the first principle that we're looking at today is principle 7. So we've already passed the halfway mark, frightening, and it's about patterns. And we're going to talk about patterns in nature. And the principle is design from patterns to detail. Okay, so Clovis, I'm going to turn you off so I don't get an echo. Okay, but so we've already been talking about how, in some way, permaculture is about learning to read the patterns. That every circumstance that we come across in nature is unique. They're always different, but actually they conform to patterns. So the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, that's a pattern. And every Monday is not the same, but there are aspects to Mondays which are the same. The beginning of the week and whatever, however it is that we organize ourselves. The months of the year is a pattern. It helps us navigate through time and space. We know what to expect when it's January or March or December, because there are characteristics of every March and December which are the same. But of course, December 2019, from one year to the next is always very different. So but we navigate where we can find where we are by looking to the bigger patterns. Okay, so in nature, the same kinds of basic patterns occur again and again and again. And there must be a reason for this. We don't have to understand, but it's an interesting thing to ask ourselves. When it comes to designing, often we want to repeat the same kind of patterns and processes occur again and again. So design is also a process, it's also a pattern. And we're going to show you and bring you into the pattern language of how we design, how we create new things with particular outcomes in mind. And so this is the beginning now where the first 6 principles of permaculture, the first things that we've been working on, are all actually our observations of the natural world, where we observe and interact our own observations, the whole catch and store energy, obtaining a yield, to see the world as systems, to see systems and realize that those systems self-regulate and self-correct, that the world, that we need to use and value natural resources and services. And we looked at things like compost toilets and slow sand filters yesterday. I introduced biochar as a concept. So we're thinking about these natural processes and things that we can value. And number 6, the idea that in nature there is no waste, produce no waste. We had the icon of the worm and the idea of that nature has these endless cycles. Okay, so we now need to work with those observations, and we work with those observations by fitting them into patterns. So let's see how we go with this. And yeah, I hope you enjoy this presentation. Pattern language is deeply embedded in nature. When we look at anything, a flower, or any kind of natural thing, we come to see that there are patterns hardwired into that. So this is a kind of cabbage. It's a kind of a broccoli. And the pattern that it has is what we call a fractal pattern. A fractal pattern is the same at any scale. You can look into this really closely, or you can stand back, and what you start to see is the same pattern repeated again and again and again. Nature does this a lot. We can learn from this. So this is what we call a pattern archetype, because we see this pattern is itself as a pattern. It occurs many times. We'll come back to this. This is called a fractal pattern. This is the underside of a lily leaf. It's a plant that the leaves are very large and they float on top of water. So this has been turned over. So we're seeing the underside of the leaf. And look how clever it is. Look how these ribs they make it strong. And then there's sort of the circular structures, again, make it strong, rather like a spider's web. You think about what makes a spider's web strong and functional, that patterning, it's the same in this leaf. Now this leaf floats on the surface of the water. So as this plant respires, as it photosynthesizes, the carbon dioxide it's producing comes out on the underside of the leaf and it traps in these little pockets. So the leaf literally can float on the water and be really, really strong. That's design. That's a nature's pattern, if you like, expressing itself in a way in which it fulfills a function. So we're always interested to think about what functions various patterns help us fulfill in design. Okay, so obviously these are nature's designs. This is how nature's expressing itself. No one's built these. Soap bubbles. When you squash spherical things, round things, when you squash them together, you get, look, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You get a hexagon. There's a hexagon, a six-sided figure. 1, 2, 3, 4, 5, 6. And fives. 1, 2, 3, 4, 5. If you squish circular things, spherical things together, then they only fit together when they make shapes of 5s and 6s. Interesting. Let's just find that interesting. We're just observing nature. Again, like on day one, observing nature. This is what nature does. Okay, and we're interested in these things as permaculturalists. Think about how we can work with them. This is the eye of a fly. And we've got a curved surface. And you can see in the structures that we've got lots of hexagons together. So that same kind of pattern formation is happening in different things. Soap bubbles, eye of a fly. This is an interesting one. This is the tail of a what do you call it? It's not a lizard. It's a chameleon. A chameleon. It's like a lizard. And look how the tail, when it curls into itself perfectly, into a spiral. That's another very important pattern that we see again and again and again. And then also notice that the surface of the skin has the scales are kind of 5s and 6s. The way that they fit together, it's the same kind of patterns that we're seeing in these other shapes, yeah? So there's a reason for that, and that's because it works, it's effective, it's functional. So this, as designers, as people interested in how nature expresses itself, we can learn from looking at these patterns. This is, it's a kind of sedum. It's a succulent plant. And it doesn't really matter what it is, but it's a very familiar pattern, that flower pattern, the petals. And to think about the numbering of them and the way that they sit together. It's beautiful. It's a natural form. Again, something perhaps that we can learn from. This is a dahlia. Look how we've got lots of individual little patterns repeated again and again and again to create a sphere. This is a sundew leaf. This is a plant unfolding, and these little drops are sticky, and if a fly or insect lands on there, it gets stuck and the plant eats it, digests it. But again, just like the tail of the chameleon, it curls in on itself. It's a perfect spiral. Bees, or that's a wasp, sorry. But look at the hexagons fitted together. Again, strong shape. It gives a lot of strength, that shape, with the minimum amount of material. Nature's very efficient in the materials that it uses. This is a millipede, an insect. I'm sure you've seen these. And look how it can curl up, and also is that where the legs are, its underside, that's its most vulnerable part. So because it can curl up like that, it can protect itself. So again, thinking about functions of design, things are like they are. So a very key idea really in nature is this, is form follows function. I'm going to say that a lot. And in other words, what that means is it doesn't really matter what it looks like. In nature, design is not about what it looks like. That doesn't matter. What matters is, does it do its job? Does it fulfill its function? And obviously, the armor of this millipede, its function is to protect the insect. Does it work or does it not work? The fact that it looks really pretty is irrelevant. We're seeing the same sort of patterns this is a cactus. So these are just some of the pattern archetypes that we see in nature, and they're just a collected set of observations to go, interesting. Now let's try and categorize some of these patterns so we can actually identify these pattern archetypes, and we can talk about them. Let's give them a name. So the first one, and we see this a lot in nature, is the branch, the branching pattern. Look how the stem divides and then divides and divides again. It looks like a tree or a river or something like that. This is a river delta in the Baltic. And look how as the river flows into the sea, what you're seeing here is a very large river entering the sea. The river's carrying silt with it in the water, but as the river slows down, it deposits that silt, and that blocks the channel, and then so the sea, then the water pushes to the side, and so over time it moves around, and it creates this ever branching pattern that's in our lungs. But in this tree, same patterns, whether it's in a river estuary, in the human body, or in this tree. This is called the dragon tree, and it's from the island of the Canaries. And look, there's a very simple mathematical formula behind this. And actually, looking at this tree, there's some important ideas that we learn about nature, which is, in nature, things can start very simple. Here we just have one branch, the trunk of the tree. And it reaches a junction and it becomes two. But the distance halves. So look, there we go from, we have and then it splits again. And it keeps all it just keeps doing is subdividing. And subdividing and subdividing. And we've moved from one to many. We've moved from simple to complex. Now you could plant the same tree in the same space and it would grow to a unique shape, because even though the formula is very simple, is one subdivides to creates two, and then each one of those subdivides to creates four, is as the tree is growing, it's being shaped by nature, shaped by the wind, shaped by the rain, being eaten by birds, hot days, cold days, wet days, dry days. Because the conditions are never exactly the same. The shape of the tree reflects the uniqueness of that time. So this is why, simplistically, this is why every person's fingerprint is different. There's the individual, and then this is the expression of all of those different options and changes that could have happened. And then this final shape you arrive at is the uniqueness of that particular individual. So within pattern formation, I want you to think about how there's a very strong relationship between simplicity and complexity. Simple, complex. Singular, many. But they're totally related. So here's an idea I want to give to you, is the formula for permaculture is quite simple in terms of mathematics. We're giving you 3 ethics, and to achieve those ethics, you use 12 principles. That's a very simple formula. But each one of you is different. Each one of you is operating in a unique place. You have slightly different skills, different abilities, different life experiences. You have different materials to your available, and you work with different people. So even if you're taking the same ideas and working with them, you're actually going to create create unique circumstances. Okay. Simplicity, complexity. Every decision that you make creates a unique environment. Think about that. Every decision the tree made creates a unique shape, but it all fits the same pattern. So you could see that and go, yeah, that's a dragon tree, but it's not like any other dragon tree. In the same way as you're not like any other person. Okay. Think about how these trees interact and how the pattern expresses itself. Look, at one point when this tree was young, this branch was growing this way into a space where there was light. This branch was growing this way. They were growing both into the same space because there was available light there. And then as they started to shade each other out, they moved back and go out the other way. So we can also think about how, as patterns are forming, things are actually interacting with each other. So it's expressing itself as it develops. So as above, so below. This same branching pattern in the roots. You see branching pattern, and again, is what's the tree trying to do? Why is it having that shape? And it's because it wants to create as much surface area to catch and store the energy of the sun. So to create something that divides and divides, you have twice as many. You go from 1 to 2 to 4 to 8 to 16, but each time you shorten the distance. And in that way, the tree is covering as much area as it can as quickly as possible. Think about these simple branching patterns. This creates as much surface area to catch the sun as it possibly can. And it's doing that by just repeatedly branching. The same thing's happening in the roots of a tree under the ground. This pattern's interesting. This is the action of water flowing over sand. Now, we showed those pictures yesterday about gully erosion, and we talked about how we plans to reduce gully erosion. Now, interestingly, we have Rose here who's working on a project in a school in Rwanda where they have exactly this problem. They have big gullies eroding across the school grounds where rainwater is accelerating over the ground. So this is what we would call a rill. These little feeders where the water starts to come in, and then we get the gully is this big excavation where the water has shaped the sand. Obviously, this is on a very small scale, but these patterns occur. This could be the side of a mountain. You could be looking at something enormous. In fact, you're looking at something very small. But the way that water drains off a landscape creates shapes and patterns that we always recognize. So there's, again, our branching pattern. A river might look like that, the way that it drains a landscape. Okay, so we're interested in, so this is and this one is doing the opposite of the branches of a tree are spreading out, and on this one it's coming together, but it's creating the same function. It's nice to see patterns in sand, to think how different things interact with each other. So again, this is almost a way in which patterns are hardwired into nature. The water isn't conscious of the shape it's making. The sand isn't conscious of the shape it's in. But there you have it, happening all the time. Nature wants to express itself in patterns. So we saw this lobed pattern as well. We saw it in this dahlia. We saw it in other aspects. So let's explore that. The lobe pattern, it creates a lot of surface area. This is in your gut. This is to help absorb your food. You have these structures in your gut which creates a lot of surface area so you can digest your food. I looked at that shape and I thought, oh, that almost looks like a city with skyscrapers. Lots of individual elements. So this lobe pattern is individual elements clustered together that creates, again, an enormous amount of surface area, a lot of places for people to live and work and explore, or lots of places for bacteria to live and work and explore. So it's interesting how these patterns reoccur in different scales. This is a dry stone wall. Something which we do a lot in our farming. It's an old technique that we don't do anymore, but we have these as a legacy everywhere in UK. When they're farming the fields, they gather all the stones and they build a wall out of it around the edge because it protects the field from the wind. But they create very, very valuable habitats for plants. Look at these mosses growing on this wall. It loves it. And but also for lots of little insects and small mammals. They can live inside. It's like a block of flats almost for wildlife. So they can be very good structures. The leaf of a kale plant, again with all these lots of individual little lobes and shapes, creating again a lot of surface area. The leaves of pumpkin plant. Again, it interests me how the plant works as a whole, and look how each leaf is responding to the energy of the sun, and they're perfectly positioning each other to catch as much sun as possible and not shade each other out. So again, nature's patterns. Here's a simple permaculture sort of idea. We're interested in edges. An edge is where two different environments come up against each other. And we always say you get a unique set of circumstances at an edge. So imagine this is a garden, a field, or your plot, and there's the path that crosses it. So if you want to walk from this side to this side, the straightest, quickest, easiest way to do it, obviously, is in a straight line. But what's been observed over time is that in a garden, when you walk along the path, the gardener notices what's happening in the field more next to the path because it's close. You can see it. You're walking past it every day. So you're more likely to, if you see a weed, to pick that weed up. If you see a fruit, to pick that fruit and eat it. You're more likely to interact with your garden closer to the path. And the edge of the path is this very interesting environment where, let's say the path is the human environment and the garden is the plant environment. And the edge of the path is where those two worlds come together. So you, the gardener, the farmer, you see and interact with that more. You spot more weeds, you see more opportunities, and that plant just needs looking after or whatever. So if we make the path curved, it's still a path. It still has the function of a path. It still gets us from one side of the garden to the other. But this one now, it's longer. We've extended the edge. We've maximized the edge. So now when I walk through this garden, I'm going to interact with more of the garden. If you get me, I'm not just coming through in a straight line. I'm now exploring this bit, and I'm exploring over here. I'm exploring over here. But there's a problem. With this path is excellent for gardening, but it's very annoying if I just want to carry a lot of material from one end of the garden to the other, because I've got to then do this long journey. So in permaculture, we like the idea of a keyhole path, because then we're getting both functions are happening for us. I can travel from this end of the garden to this end as quickly as possible. There we go, straight line. But I have these keyholes. So the idea is, when I'm standing here, I can garden, I can reach 60 centimeters before I fall over. I can reach out about 60 centimeters. So if you place these keyholes 1.2 meters apart, I can stand here and I can reach all around to garden. And then I can walk here and I can stand here and I can reach all around to garden. So I can access all of my garden, but I don't have to stand on the soil. Remember, we don't want a compact soil. We want to keep it open and full of air. Remember from your test yesterday, healthy soil is 50% air, and it's not going to be 50% air if you keep standing on it. So, and again is, we can dig the topsoil away from where the path is, and we can put the topsoil on the bed. So we've got more good soil for the plants, and you're standing on the subsoil, which is not as valuable. So we've now, by arranging these things this way, we've still got the function of a path that gets us from A to B quickly. But we've also got the function of, we can now access every part of the garden without standing on it. So we've created edges, we've created as much interface, as much connection between me, the gardener, and the garden. Okay, so that's an idea. Maybe a keyhole bed might look like that. Now, a keyhole path rather. We have a special keyhole bed design, which I think you've seen. And again, that's just exploring the same idea. The keyhole in the bed is what's allowing you access to reach in to do the gardening without standing on the soil. So we're designing for the plants and for the person, and we're using very simple patterns. So look, here's our keyhole pattern again. The gardener can stand here, and he can reach all around. So I think you've already had the idea of a mandala garden introduced to you. And a mandala garden is simply the same pattern that's repeated many times. So we can make this one bed and decide, oh yeah, we're happy with that. We'll make another one, we'll make another one. And we can repeat that pattern in a repeating pattern. Some of the refugees, when we went back to visit them in 2018, they'd made a little keyhole bed and then we came back some months later and they'd repeated it again and again and built these lovely complicated shapes. So this is fun. But what you're actually doing is you're maximizing the relationships between the gardener and the garden. You're making interesting shapes and patterns so that there's edges. You're coming close to your garden. You can observe it. You can tend it. These are very simple things, and also you make it easy then for other people. They can see, oh, that's the path. That's the garden. That's the part for the plants, and that clearly is the path for the people. Putting things in straight lines. These are planted, say these could be tree plants in the same space. By having everything in the same line, in the same straight lines with the same spaces, means we can only actually fit 70 into this space. Whereas offsetting them, we've got a better, there's all of these spaces here, that's space, space, space. By offsetting them, we can actually fit 86, wow, another 16 into the same space just by how we arrange them. And then another thought is, if one of our concerns is wind and how wind might flow through a tree planting, we might want it to act as a windbreak. With straight lines, we create corridors that the wind can whistle through. By offsetting and we're creating much more friction. The wind's got to sort of wind its way through, and obviously the trees can sway around and take up some of that energy. So also another consideration, just patterning means that we can have more elements in one place, should we need to do that. and also is we can reduce the flow of let's say air through that, again by spacing. So it's about designing for function. Form follows function. We should try and make things look like the way that we, to fulfill the functions that we've identified in advance. Again, back to the eye of the fly, this very interesting hexagons joined together, making a curved surface. Okay. Okay, we'll come back to that. Okay, so now I'm going to introduce you to the next pattern. This is fairly mind-blowing. I think it's really, really important. And we have a series of numbers. Is that going to be back to front, I think? You can't see that anyway. All right. Well, that's back to front because the way the camera works. Okay, so look. Here's a series of numbers. We have 0. If we add 0 and 1, we get what? 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 8 is 13. What's the next number? If 5 plus 8 is 13, what's the next number in this series? Come on, can anybody tell me? What's the next number in this series? This is called the Fibonacci series of numbers. And wherever we go in nature, we see this pattern. It's everywhere. And it's generated by very simple mathematics, which is that you take the one number and you add it to the next one. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 5 is 8. 8 plus 5 is 13. I want to know what the next number is in the series. Who can tell me? What comes after 13? Is anybody following this? Tell me, Clovis. You have to unmute. Okay, I got it. Yay, well done. So Rose has just come in with 21. It's the next number. Because that's 13 plus 8 is 21. And it goes on. So 21 plus 13 is 45. It's 44. So, and the this series of numbers gives us a spiral every time. 1 plus 1 is 2. 2 plus 3 is 5. 3 plus 5 is 8. If you draw a line that bisects the this like this, halves the space, then we get a spiral. And this is the nautilus shell. This is the shell of a snail. And what we get from the spiral, from this shape, is something that is functional at every scale. So think about this. When a snail is born, really tiny little snail, the shell is also really small. And as the snail grows, the shell, which is only attached to it on the back of its mantle there, is slowly growing. And as it grows, it revolves. So the shell of the snail is the right size for the snail at any stage of its life, and it's functional. It works as a home at every size. Now this spiral, this idea of this spiral, something that works when it's really small, and then as it gets bigger and bigger, it still works, it still performs the same function. We're very interested in this because this represents incremental growth and incremental design. And an increment just means in small steps, very small steps. So what we imagine is, how do we change the world? How can permaculture transform your life? How can permaculture make you very successful? Well, the answer is very slowly, with small and slow steps, with increments. If we get one thing right, we can build on it, and we can do the next thing, and it gets bigger, and it gets bigger, and it gets stronger. And we move step by step by step. We can't go straight to, from tiny to really big is not sustainable. The lesson from this is even our own development is a slow process that builds on itself in increments, in small steps and stages. So your permaculture journey is also a bit of a spiral, and we're going to explore that again as an idea later on today, I think. So thinking about these patterns again, we'll come back to the spiral because it's a very important pattern, but also as we discover that this Fibonacci series, this number series is in everything. It's in this crazy looking vegetable. It's in the universe. Here is our spiral, and look at the arms of the spiral. They're the same. Go all the way back. Oh, we lost it. Sorry. Anyway, we'll see it. We see it again and again and again. There's a leaf unfolding, a fern unfolding. But here's another thing. Okay, so imagine this. What's really fascinating, honestly, is if you get the most powerful telescope and you look into the sky at distant galaxies. That's what this is. This is the Andromeda galaxy. It's a spiral. And you look in a telescope and a microscope down at tiny little things, and you see the same patterns. There's something in that. This is a leaf unfolding. It forms the spiral Fibonacci series, the same mathematics. Even the way your hand works, because again, your hand, it spirals. It you know, it can curl on itself in the same way as that tail of that lizard. And look, the phalanges of your hand, 2, 3, 5, 8, relative distance. It's the same. It's the same pattern. It's a Fibonacci series. This is in art. When we see these patterns, they're pleasing to the eye. They call it the golden ratio. It's something that's very pleasing to ourselves aesthetically about certain kinds of shapes and patterns. Okay, here's an interesting idea, another pattern. This is a herb spiral. So the idea of this is to create as much microclimate, to create little small differences in conditions, as many differences as we can in a small space. So then we could create the conditions that suit lots of different kinds of plants. It's just a fun thing. But if you think about the top, because it's domed, shaped like this at the top will receive rain, but that rainfall will go down because water goes downhill. So you can plant the plants at the top that like dry soil, and the plants at the bottom that like wetter soil. If this is in the northern hemisphere, the sun's coming from the south, so we can put the plants that like the sun, more sun at the front, or the plants that are taller and can reach the sun at the back on the north side. Maybe the wind comes from this side's more sheltered. We can explore environments and create lots of little differences, microclimates just through shape and patterning. If you think about how that's a design to create a lot of different microclimates. Okay, I like this pattern. I've thought about this a lot. I think it's supposed to represent the sun and the moon and stuff. This is obviously on the Nyero rocks, you know, and if you look on the 1,000 shilling note, it's on the 1,000 shilling note in Uganda. I think it was the Twa people, I think, who did this maybe thousands of years ago. And I don't know what the pattern is saying, but it looks very interesting to me. And there's something again about pattern languages. Whoever painted this rock, the Nyero rock paintings, whether it was 2,000–3,000 years ago, they were trying to communicate a complicated idea. They didn't use words to explain it. They used a drawing, a pattern. And to me, that's really interesting. And because that pattern can communicate really complicated ideas, much more than a few words can. Maybe it's about seasons. Maybe it's about the self within a community, within a world of work, within a wider natural world, and how we relate to the outer world around us. I wondered if this was the male and female principles, the sort of the creative forces that bring about new life within the world, the seed within the individual, within the community, something like that. I don't know. Anyway, it's just interesting. It's beautiful, and it's certainly talking of it's exploring relationships, I think. The net, another very common pattern. We've all seen spiders' webs. We all know what they are. But what I always like to say is, we all see a spider's web and recognize it, but every spider's web is different. They're all unique. So we learn to read the diversity and complexity of the world by seeing the pattern behind it. And in this case, the spider wants to create a trap to catch flies. So it's filtering, it wants to filter as much space as it can, but with as little amount of material, which again is a beautiful, elegant design. The size of these holes relate exactly to the size of the kind of insect that the spider hopes to catch. So again, the form follows function. The spider's using its energy and its resources, its ability to spin web, to set a trap to catch a particular kind of thing. So the place where it is, the size of the holes, the season, all of that would be part of the spider's strategy. In fact, they're doing some research into spiders, because they are kind of interesting things, is that they think that scientists saying that the shape of the web is almost a map of how the spider is thinking. It's an externalization of the thoughts of the spider. I think it's fascinating. Anyway, okay. But it has a functionality. So look, we were building this structure. This is a community garden project I was working on a few years ago. We wanted to build a low impact structure with some volunteers, as much as a team building exercise actually, but we also had a nice space to use. And we made a reciprocal beam roof. There's me holding up a beam, and the way that it's made is the first beam, there it is propped up on this support. Then the second beam sits on top of that, and the next one sits on top of that one, and you go all the way around until every beam is sitting on the one before it, and then you can kick out the support and it all locks into place. And you have a very strong structure in your roof, but it doesn't need a central support. So you have a nice big open space inside. So a reciprocal beam roof. Well, when I looked at it, I thought, oh, it's a spider's web. All we've done is recreate that shape. So this is creating as much strength with a minimum amount of materials. And so so that becomes a design archetype. Or we can follow that pattern, and in our roof, we can go and create a strong roof without having to use loads of materials. That's how patterns shape and inform design. Just looking at the ripples on water. This is mycelium. This is mycelium magnified many thousands of times. This is what it looks like. It's a web of almost of information. These are pathways that the fungus are exploring to get as quickly as it can from one place to another. Look how they bounded together to create little highways. It's fascinating, so complex. And then this is what a computer system looks like. We're trying to join lots of different things together, and what happens? Oh, we create the same pattern. Mycelial patterns represent information in some way, in the same way that computer systems represent flows of information, with nodes and hubs. So look, the flow of information, but where there are crossing points, we have servers, we have, like a hub. And then that turns out that happens in mycelium too. Look how we've got hubs and crossing points. This is mycelium growing between two pieces of wood, and look at the pattern it's created. It's like it's tried out. It grows in one direction, and if it's interesting, if it's interested in what it finds, it starts subdividing and creating more surface area, and therefore it can interact with that environment more. So these are webs, surface of water, mycelium, computer systems, computer networks. That's the internet. These are the relationships within an ecosystem. These are energy relationships within an ecosystem. This is in a little pond. There's a leech. There's a fish. And then on the next layer, each one of these are different trophic levels. So we've got our plankton at the bottom, being eaten by zooplankton. So these are plants. These are little insecty things, and then those are being eaten by small fish, eaten by big fish, and then we've got the predators at the top. And this is just mapping the relationships between all of these elements in a system. So think about your own webs that we weave through knowing people, through interacting with people, through trading with people. We create a web of interactions that if you mapped it or draw it out, it would look like this. And in permaculture, what we've realized is, in terms of understanding these webs, we're interested in these nodes, these places where there's a crossing. They could be represented by a key species, or a key person, or a key source of information. But wherever there's crossing points, multiple crossing points in a system, we get these hubs and nodes. So if this mycelial mat here was a map of permaculture in Uganda, there's Kumi Happy Home, there's Clovis, there's Rose over in Rwanda. You're becoming nodes of learning. You create connections to the people around you, and you share your knowledge with you. Look, here's me communicating to you down this line, and then around you, you share that knowledge out to lots of other people. This is how ideas spread. This is a map of intelligence, okay? We are living in a time of crisis. We're living in a time of change. The world needs to evolve and grow to new ideas. How do those ideas spread? Through nodes. We create a connection from one node to a next. Look, let's go back to the computer system. Here's one node, and here's another one. We can send information, support, knowledge to this place, and then from here, you can connect to all the people around you. You're creating a node, you become a node, you create a permaculture community around you. This is how we work. This is what we call a diffuse, multi-centric system. There's no leader. There's no one person in charge. Each one of these can generate a new system by itself, each one of these nodes. Give enough information to Clovis, he can go out and start a permaculture center and create nodes all around him, create a network of connections all around him. And then each one of those can then themselves become a node. This is what we're trying to do with Sector 39, is I'm interested in how do we accelerate change? How do we identify people who can themselves become a node, that can become a little central point that can educate those people around them? Because we each then can become active in this wider network. Plus, this network mustn't have to ever rely on one person. So this is not about me. It's about me transferring information to you so that then you can then become a node in your own community, within your family, within your community, within your work, within, you know, and then maybe ultimately within across the whole globe. You might become a world leader in permaculture, who knows? But it mustn't depend on any one of us. It needs us all to realize that we're somehow connected and we're somehow exchanging in the same way in this mycelium. It's exchanging nutrients. It's exchanging also antibodies and sugars and many ways kind of information and resources and energy. So what are we sharing right now? Information, resources, and energy in the same way as the fungi, the mycelium is functioning. Okay, so these lines represent our relationships, and these nodes is you, me, Ali, Rose, Vicky, Irene, etc., etc. Okay, you become a teacher, and then your job is to create those same nodes around you, because we have to accelerate these ideas out into the wider world. That's our mission. That's what we're trying to do. And we change the world, remember, by firstly changing ourselves, by having our ideas, taking them on board ourselves, working through zone one, through ourselves, to meet our own needs. And then we start to help meet the needs of other people, and understanding that we are operating to serve the planet, the biology of our world, okay? These are important ideas I'm giving you. I want you to think about them very deeply. So we're thinking about pattern archetypes. This, when we get to this web pattern, to this mycelial pattern, I think this is the master pattern of the universe and of intelligence and knowledge and how people grow and share. Okay, so we can work with this. This is just weaving out of rushes for, and looking how creating a simple structure, we can weave around it, and as we weave around it, it gets stronger and stronger and stronger. Something about that the same. There's real strength and resilience in this pattern, and there's a strength of functionality in this pattern. Okay. The scatter pattern. Random, just, you know, chuck it out there. This is one of nature's favorite patterns. Look at these seeds blowing on the wind. The plant has no conscious thought about where those seeds are going to land, but what it knows is if it saturates them, they're going to blow everywhere, and somehow some of those will lodge into the right place. It's the idea of just broadcasting seeds on the ground. So these are not great pictures, actually. I want to introduce an idea that's an experiment that we've been working on. Is we call it the poly-veg bed. Poly-veg, poly as in many. And in this bed here, this is a seed bed that we've carefully prepared. We've added some compost and some water. We've allowed it to germinate, anything to germinate in the sun. And then we've come along with a hoe, and we've just got rid of any weeds, and we've made sure that no other weeds are germinating. Then we have saturated the bed with seeds of everything is edible. We've put in lettuce and herbs and cabbages and mustard and tomatoes, I think onions, all mixed together, and from seeds that we've saved ourselves, so that we know that anything growing in this bed is something that we planted. And as it grows, look, we've put little clusters in accidentally. As it's growing, you thin it out. So you just, this is nature's way of farming, isn't it? It throws out all the seeds there, and whatever happens, happens. So as a gardener, you just thin it out and you select the ones that you want to become adults, and the other ones, you know, you can even eat them, even when they're really small. Look, there's a pea there, there's radish there. So this is an idea of, you sow your own weeds. You sow a green manure of edible, something like mustard, around your plants. So the soil is full immediately, and nothing else can come in and take over. And then you just keep thinning it as the other plants grow. Okay, wave patterns. There's something amazing about water. Something and the patterns that it makes. Flows of rivers, flows of in weaving. Again, patterns in waters, wave patterns. How about energy as a wave? Electricity comes as a wave. Energy has a flow and it has a shape to it. So something interesting about that to notice. That's your heartbeat. That's the rhythm of your heart. It's also a wave. So there's something about that that's very important, way that our heart works. And just to close off is, there's so many ways in which people now have started to work with these patterns and realize, look, if we take this into a very pure mathematical form, because of course in nature nothing's perfect, nothing's exactly, all of these patterns are archetypes. You never see them exactly repeated. Everyone is unique, right? But we can still see the underlying pattern. We can recognize the same way as we recognize a spider's web, even though everyone is different. Well, if we start to bring these ideas into mathematical exactness, so there's your 5-sided figure, your pentagon, and there's your 6-sided, your hexagon. If you join those together and alternate them, you get a perfect sphere. You get a perfect sphere with the minimum amount of materials for the maximum strength. So you can build with that. But what's interesting is there's pollen grains that look exactly like this. This pattern is something which occurs in nature. But you can take that. This is cooling rocks. It's the Giant's Causeway in Ireland. Same pattern. Snowflakes. When water freezes in the air, when it's falling through the air and it freezes, it becomes a snowflake. It always makes a 6-sided figure, always. But they're never the same. And look how different they are. It's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. Every one. But they're so different. There's something in that to learn. I don't know what it is, but it's why we are all different from each other. It's why your fingerprint is different from my fingerprint. But we're all the same energy, but shaped by the same forces, but we're all unique. Something very beautiful and special about that in nature, and we recognize that in ourselves. We can think about the shapes of plants as patterns. This is a bramble, common plant here. It grows in threes. The leaves always grow in threes. This is a nettle, another very common plant here, and they always grow in opposite pairs, always even numbers, 2s and 4s. How about inside an apple? You get 5. 1, 2, 3, 4, 5. Plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that a Fibonacci number? No. Interesting. Shapes and spheres in construction. Again, 5s and 6s. This is in the British Museum. They've used the same idea to create a domed roof that connects a circular building to a square building. Really interesting shapes and mathematics. This is a sea wall, a defense against stop the sea eroding the land. And look what shape it is. It's hexagons joined together, what we saw at the beginning. Again, that gives you really strong structure and for the least amount of material. If you cut through your bone and it looks like this inside, your bones are sort of a bit like the bubbles. Right back to the beginning. Soap bubbles. This makes a strong structure. A small amount of material, but they're all in contact with each other. All those surfaces are touching each other, so it becomes strong. Sorry. There's our C defense. Where is it? This one. Again, same pattern, but in art. Same pattern, but in and again, I guess art and sport. Interesting. So this is a chicken wire fence. What's the function of chicken wire? Well, it's to create strength, to obviously create a barrier for the chickens, but using the minimum amount of material for the maximum effect. So this is a function of design. Whoever designed this chicken wire, they thought about the size that it needs to prevent the chickens from causing problems, and the choice of material, and then how to use the minimum amount of material to create the maximum effect. These are design decisions. Okay. Let's just go back to this idea of this diffuse multicentric pattern. Imagine this as an information system. This is the chain of command, or this is the spine of a centipede or a caterpillar. And if there's any disruption, and these are all of the subordinates. So these are the control subordinates. This system is a bit like political systems with big leaders or something. But the problem is that if there's a disruption between these, hello, boss. Hello. Okay. If there's a failure, if there's a break between here and here, there's a catastrophic failure, because then now this system doesn't work anymore. If there's a break between here and here, then this one can still connect with this one by going a different route. There's other options. So this makes this pattern's really strong. If we lose one of these nodes, if this is a node, if we lose one of those, we can still communicate around the other way. In this one, if one of these nodes is broken, then this element can't connect to this one. This can only go through this line. There's no other way through. This one, it can go that way, or it can go that way, and that way, and that way. It has choices. So, and then with our mycelium, actually, it's almost like this is how a computer program works, is you have layers on top of each other. So there's like a highway going across the top of big connections. But if there's a fault between here and here, then there's a route down through and come up and come a different way. So again, that's essentially what's happening here. Look at these pathways that are sitting on the top, and then underneath there's much more complexity underneath it. So this is a good model for design. And this is what makes things very strong and very resilient, is lots of different connections. And that's what we're trying to achieve. Again, this is mycelium on a sunny day. This structure here is lots and lots of tiny little filaments creating surface area. Again, remember, 8 miles of mycelium in a cubic inch of soil. Think of that as that complexity. So what's happening here is the mycelium it's weeping out, it's exuding an enzyme. So mycelium digests its food outside of the body. So it gives off an enzyme. That enzyme is literally liquefying. This is in wood, growing in wood chip. It's liquefying the wood, and then the mycelium will then absorb that back into its structure again. Surrounds something and then exudes enzymes and learns how to digest the thing that it's working with, and then it turns it into its food. Very, very clever. This is the building block of life. There we go. So there's some thoughts about patterns. It's now 9 o'clock. So do you want to have a short break? We'll just have a short break, and then I'll come in and I'll talk a bit more about, or have I used my time? I've got another hour, haven't I? We're going to talk a bit about design, if that's okay. Well, we just have a quick short break, just 5 minutes. I need a break anyway. I won't be long. Okay, so welcome back to part 2 of our morning lecture. Today we are looking at principle 7, and we'll move on to look at principle 8 later on, but let's stay with principle 7 for now. And the statement is design from patterns to detail. Now, I've said this many times already, this idea that we start with the overarching pattern. We learn to see the pattern, and then from that we zoom in on the detail of the particular unique place that we might be trying to design with. And there's a saying, can't see the wood for the trees. And that's an idea, simple idea that we fail to see the individual for the bigger pattern, or we fail to see the bigger pattern for the individual. I can't see the forest for all the trees in it. Because we're interested in systems in permaculture. We're interested in seeing a bigger picture. We're inviting you always to see the overarching pattern. So not to focus on the individual tree at this stage, but to see it as part of a forest. You can't see the wood for the trees. And again, we talked about this spider's web. You always recognize, yeah, it's a spider's web, but that spider's web is unique. It never will have been one like that exactly before or ever again. So there's something wonderful. So let's go into explore the ideas. By the correct placement of plants, animals, earthworks, and other infrastructure, it is possible to develop a higher degree of integration and self-regulation without the need for constant human input. If we put things in the right place, they work. If we put them in the wrong place, they don't. For example, we might observe that chickens like to scratch and turn. They're always scratching. And in the wrong place, they can cause a lot of damage. They can mess up your vegetables. In the right place, chickens really are forest animals. They can be used to harvest litter, regulate pests, eat the rotten fruit, eat the bugs. In the right place, they can be very useful. In the wrong place, they can be very destructive. Herbaceous and woody weed species in animal pasture systems often contribute to soil improvement, biodiversity, medicinal and other species. Appropriate rotationally grazed livestock can often control weedy species without eliminating them and their values completely. Oh, we've lost you. You've gone. I shall pause. Okay, are we ready to start again? We'll carry on. So we just had a look at we had a quick look at our principle. Let's see this message. Okay, so welcome back. I'm talking about seeing patterns and working with patterns. I'm going to show you another pattern. Here's our journey to making decisions. How we might come together, firstly, perhaps as an individual, but how we might come together to other people to start working out a plan. We're going to challenge you to come up with a personal action plan, to think about stepping stones that you can start making that's going to help bring permaculture into your world, into your community. And we're going to be looking at this design process a little bit over in this session. So one thing I want us to think about is at the heart of the process of change, of wanting to achieve change in the world. Permaculture is about how we deal with change, how we solve problems. To work together as people, we need to understand that we're operating from the same values. I think that's the thing that brings us together. So once we can commit to an idea of earth care, people care, fair share, setting limits, investing surplus to develop towards mutually beneficial goals, then that's really interesting. Then from this point of consensus, if we can be joined together in our ethics, our values, then we can then begin to explore together what might be our long-term goals. Where do we want to be in 10 years' time? What's your objective? What do you hope to achieve over the longer period? So in the same way as I said at the beginning of the PDC, your ethics are like a long-term steering mechanism. I don't know exactly where I'm going or how I'm going to get there, but I'm going to operate within these values as my method of getting there, okay? And then I might think, well, where do we want to be in the longer term? What's our longer term objective? Oh, they've gone again.